Okay, great. So we just talked through essentially what we're trying to accomplish when we take a partial derivative. Now what I'm going to do is I'm going to try to walk us through how to actually take that partial derivative. So as I said in the last video, if I wanted to take a derivative for a specific value of y, it would look exactly like what we would do for a normal single variable derivative, right? So if I wanted to know the derivative of f of x comma 1, for example, actually, I'm going to do this for 2. Derivative of f of x comma 2 with respect to x. What I would do is I would say, well, this is going to be the derivative with respect to x of 2, our value of y, times x squared. This makes sense? And then using our standard derivative rules, what we would say is, well, the derivative of 2x squared is simply going to be 2 times 2x, right, which of course is going to equal 4x. This makes sense? So if I wanted to know the derivative of f of x with respect to x at some specific value of y, all I would do is plug in the number we have for y into the function and I would get this answer. Right? If I did this with a different value, let's say that I said of x comma 1, right, this is going to be the derivative with respect to x. Of 1x squared, right, which is just going to be 2x, right, 1 times 2x. And so just as we said, right, the rate of change is going to vary depending on what y is. Now, what we actually want, though, when we take a partial derivative of this function with respect to x, is we want to know the value of this derivative for any value of y, not just for some specific value of y. So what we're going to do is we're going to go through the process of taking our derivative in exactly the same way that we just did, except instead of plugging in some number for y, we're just going to leave y as y, right? We're going to say that y is some number. We're not thinking about what happens when that number changes. We're going to treat it like a constant, right? And we're going to take the derivative of x, considering y as a constant. So what this means is I can say derivative of f of x and y right, is going to be the derivative with respect to x of y times x squared. Okay. So exactly the same way as what we did when we had a 2. So then what we can do is we can do exactly what we did when we had a 2, right? We say that the y is a constant, so it just sticks around. So it's simply going to be y times 2x. And that's our answer, right? And we can consolidate it and say 2 times x times y, if we'd like. This makes sense? So what we did is we followed exactly the same procedure we had when we had a specific number in as y, except that this time we used a general value of y. And as a consequence, we got a function where we know how much x, a change in x influences f of x for any given value of y. Okay, so I promised you guys a general strategy for how to take partial derivatives, and I really just showed it to you. My general strategy, the way that I would recommend doing this anytime that you're a little bit flummoxed by a partial derivative, is simply to plug in for the variables that you're not taking the derivative of, plug in some constant, solve the problem with that constant, and then go through the same process, except instead of having a constant there, have a variable that you're treating like a constant. So let's do a slightly harder example. Let's say that I had something like f of xy equals x to the 1/2 times y to the 1/2. And let's say that I wanted to know the derivative of f with respect to y. Oh, let's do with respect to x. Let's not change too many things at once. Right, so again, what we're doing here is we're going to treat y as a constant and look for changes with respect to x. So the first thing that I would do is I would rewrite this by saying, well, what if we had simply the f of x and some constant? So f of x, and let's say again, well, it's a 1/2, so let's say 4, right? Something where it'll be easy to think about 4 to the 1/2. Well, what we would do then is we would say, we would have x to the 1/2 times 4 to the 1/2. And when we wanted to take the derivative with respect to x, we would simply say, well, we're going to use our power rule. So we would say 1/2 times x to the 1/2 minus 1 times the constant, right? Which is going to end up being 1/2 minus 1 is negative 1/2. So 1/2 x to the negative 1/2 times 4 to the 1/2. And if you prefer, right, x to the negative 1/2 is the same as 1 over x to the 1/2. So we could also write this as 1/2 times 1 over x to the 1/2 times 4 to the 1/2. Okay. So this is what we would do if we wanted to know the derivative with respect to x when y equals 4. If we now wanted to know this derivative when y equals y, we just repeat the process, except without substituting a 4 in for y, right? So we would just say f of x, comma y. It's going to equal x to the 1/2 times y to the 1/2. Right? So we're going to say, well, the derivative of f with respect to x is, again, we're going to say, well, we've got x to some power times a constant. So we're going to take the power down, right? 1/2 times x to the negative 1/2 times y to the 1/2. Right? And then we can simplify this in exactly the same way as we did before, if we would like to. So I can simply say, this is going to be 1/2 times 1 over x to the 1/2 times y to the 1/2. Right? Or if I prefer, I could write this as 1/2 y to the 1/2 over x to the 1/2. Okay. Good? So what this means is, right, the way that we're going to take partial derivatives is exactly the same way that we're going to take regular one variable derivatives, right? We're going to use exactly the same tools. If you know how to take a derivative with one variable, you know how to take a partial derivative when you have two variables. However, it can be really confusing to remember which variable you're treating like a variable and which variable you're treating like a constant. So anytime that you're confused, I would recommend going through this process, even though it's a little bit annoying, right? Plug in a number for whatever variables you're going to treat as a constant to remind yourself which variables are being treated like a constant, solve the problem that way, and then repeat the process with the variable as a variable. You'll notice too that I've been using color here. Of course, that's because it's useful for educational purposes, but honestly, it's also useful for keeping track. So it might not be a bad idea to invest in a colored pencil or two so that you can do this in color, right, to help yourself keep track.